Hello everybody. In this video, we'll be discussing the concept of bond energies and enthalpy change. This is the syllabus start point. We'll start off by discussing the idea of bond energy. The term bond energy in chemistry refers to the amount of energy that is required to break a chemical bond. And when we say the word bond, we refer to things such as covalent bonds, ionic bonds, and metallic bonds. For example, let's consider a molecule of methane, which consists of a carbon atom in the center connected to 4 hydrogen atoms via covalent bonds. The average bond energy for methane is 413 kilojoules per mole. This means for every mole of the carbon to hydrogen single bond, we will need 413 kilojoules of energy to break them apart. Since the methane molecule contains 4 of such bonds, for 1 mole of methane molecule, that is Avogadro's number, 6.022 times 10 to the power 23 of these methane molecules, we need to multiply the bond energy of one of these carbon to hydrogen bonds by 4, which gives us 1,652 kilojoules per mole. This means for every mole of the methane molecule, we will need this amount of energy to break them apart during a chemical reaction. The bond energy varies between different types of chemical bonds. This table shows you some of the common covalent bonds you will see in covalent molecules, such as carbon to oxygen double bonds, oxygen to hydrogen single bonds, and the one we saw before, carbon to hydrogen single bonds, and oxygen to oxygen double bonds. You can see for all of these, they have different numerical values as each of the bonds have their own strengths and therefore will require different amounts of energy to break apart. We'll quickly talk about the definition of enthalpy, and we'll return to the idea of bond energy and discuss it in conjunction with enthalpy. Enthalpy is specifically given by the following equation. It equals to U, which is the internal energy of the chemical system, plus P, the pressure of the system, multiplied by the volume of the system. U, which is the internal energy of the system, specifically consists of 2 types of energy that we can measure in a chemical system, which contains a certain amount of chemical substance or molecules. This consists of the molecule's kinetic energy, which is measured by half times by m, the mass of the molecule or particles, times by the average speed squared. So it's really a measure of how fast these molecules are moving in the chemical system. The internal energy of the system also includes the chemical potential energy of the molecules and bonds, specifically referring to the bond energies that's inside the molecules. We call this the potential energy because it can be released when the bonds are formed as you're producing a certain molecule. We'll examine this in more detail using some examples in a moment. So enthalpy is the sum of the internal energy of the system plus the product between pressure and volume. Now, in chemical reactions, we more specifically talk about enthalpy change. So the change in enthalpy of a chemical system during a certain chemical reaction. Enthalpy change logically will be equal to the change in the internal energy of the chemical system plus the pressure multiplied by the change in volume that occurs during a chemical reaction. Now, all these factors should be accounted for when calculating the enthalpy change of a chemical reaction. But what's important to be aware of is majority of the change in enthalpy that occurs in a chemical reaction comes from the change in the chemical potential energy of the molecules, that is, the bond energy of the reactants and products. There will be changes in kinetic energy that will contribute to the change in enthalpy, and of course, certainly in some chemical reactions, there will be changes in volume that occur as well. But in most cases, the change in kinetic energy, especially at a constant temperature, and the change in volume that occurs in the reaction are relatively negligible. So they're quite small compared to the change in bond energy that occurs in a chemical reaction. Which is why you will see in a moment for most of the examples, when we are calculating the enthalpy change of a chemical reaction, we mostly consider the bond energies of the reactants and products. So enthalpy change, in simpler words, refers to the changes in enthalpy during a chemical reaction. And this value is usually measured using very accurate and precise experiments rather than being calculated. For the sake of understanding the concept of enthalpy, we'll perform some calculations in a minute for some of the chemical reaction examples. And as we explained earlier, enthalpy change includes all of these factors, but the most important factor to consider in enthalpy change is the change in bond energy. And therefore, when we perform calculations to determine the value of enthalpy change for a given chemical reaction, we will consider the bonds being broken and the bonds being formed in the chemical reaction, because these are associated with the bond energies or the internal energy of the chemical system. In the following examples, I want you to follow the following 5 steps in thinking about how to calculate the enthalpy change for a given chemical reaction. The first 2 steps involves identifying the chemical bonds that will be broken and formed in the reactants and products respectively. Whenever bonds are being broken, this is an endothermic process, meaning energy will be absorbed. Whenever bonds are being formed in the products, this is an exothermic process, meaning energy will be released. So when determining the bond energies for the bonds being broken, these will usually have a positive value because they're endothermic. When determining the bond energies for bonds being formed, these will have a negative value as they are exothermic. To calculate the enthalpy change, we'll find the sum between the positive values from the bonds being broken and the negative values from the bonds being formed. This will give us an estimate for the enthalpy change of the reaction. Let's consider the synthesis of hydrogen fluoride from hydrogen and fluorine gas, both of which are diatomic as represented by my diagrams here. Let's identify the bonds that will be broken during this chemical reaction. The hydrogen molecules contains a hydrogen to hydrogen single bond, and so does the fluorine molecules, which contains a fluorine to fluorine single bond. During the chemical reaction, these bonds will be broken, and each individually will absorb their own amount of energy according to the bond energy values. When the bonds are being broken, the atoms will be rearranged such that they will form one hydrogen fluoride molecule and a second hydrogen fluoride molecule. Each hydrogen fluoride molecule will involve the formation of a hydrogen to fluorine single bond. And when these bonds are formed, they will release a certain amount of energy according to the bond energy values. And so the total enthalpy change for this given chemical reaction will be the difference between the energy absorbed when breaking the bonds in the reactants that we saw earlier and the energy released when we're forming these product molecules. This table shows you the bond energy values for the bonds that we discussed earlier. So the enthalpy change will be equal to the bond energies that will be absorbed when breaking apart the reactant molecules. So we have one hydrogen and one fluorine gas molecule, each containing one bond. So we have 432 kilojoules per mole for the hydrogen molecule, plus 154 kilojoules per mole for the fluorine molecule. This will be the total amount of energy that's absorbed, minus 565 kilojoules per mole of energy that will be released when you're forming the hydrogen fluoride molecule. But because this is per mole, we'll need to times this value by 2 because we'll be forming 2 of these molecules. So this is the energy that will be released during the chemical reaction. Let's find the difference. This gives minus 544 kilojoules of energy. And this is for 2 moles of hydrogen fluoride molecules formed or produced. This is simply the enthalpy change of this given reaction. Now, sometimes you might be asked to calculate the molar enthalpy of the reaction, that is, how much energy is associated for producing 1 mole of a particular product. In this case, the molar enthalpy of synthesis of hydrogen fluoride will be for every 1 mole of hydrogen fluoride. Because this original value is for 2 moles, we can simply divide this number by 2 to give us the molar enthalpy value of this reaction. The unit here will be kilojoules per mole of hydrogen fluoride formed. This negative enthalpy change of the reaction tells us this is an exothermic reaction. There's a net release of energy as we go from the reactants to the products. Let's discuss a more complex chemical reaction between methane gas and oxygen gas to produce carbon dioxide and water. This is the combustion of methane gas. The bond energy values that we require to calculate the enthalpy change are shown in the table here. Before we do the calculations, let's again identify the bonds that are being broken and the bonds being formed. We start off with methane and 2 oxygen molecules. When these molecules react, all of their bonds will be broken, and each bond will absorb a certain amount of energy according to their bond energy values. When the bonds are being broken, the atoms are then rearranged to form carbon dioxide molecule, in which there will be new bonds being formed between the carbon and oxygen atoms. The remaining hydrogen and oxygen atoms will form one molecule of water, in which there will be 2 new bonds between the oxygen and hydrogen atoms, and a second water molecule with the same bonds being formed. The formation of these new bonds in the products will release a certain amount of energy according to the bond energy values. And again, it's shown in the table here. So let's first consider the energy required to break apart the methane molecule. For one methane molecule, or 1 mole of the methane molecule, there are 4 carbon to hydrogen bonds. The bond energy value for this bond is 413, so we'll multiply this by 4 to get to the total energy required to break apart 1 mole of methane molecule. Similarly, the energy required to break apart the oxygen molecules can be determined by multiplying the bond energy of the oxygen to oxygen double bond, 495, by 2. This is because each molecule of oxygen, there's 1 of these double bonds, but we have 2 moles of oxygen molecules for every 1 mole of methane. We should consider the reaction ratios. So we'll multiply this by 2 to get to 990 kilojoules per mole. Let's consider the bonds being formed in the product and the energy released associated in the process. The formation of carbon dioxide, which is a carbon atom between 2 oxygens, so this contains 2 carbon to oxygen double bonds. This can be calculated by multiplying the bond energy, 746, by 2, because each molecule of carbon dioxide contains 2 of these bonds. So this means for every mole of carbon dioxide, 1,492 kilojoules of energy will be released when you're forming it. When we're forming the 2 molecules of water, we'll be forming 2 oxygen to hydrogen bonds in 1 molecule, and therefore multiplying that by 2, we'll get a total of 4 bonds in 2 moles of water molecules. So the bond energy here will be minus 464 times by 4, which gives minus 1,856 kilojoules for the 2 moles of water that's being formed. Let's combine these results together. The net enthalpy change of the reaction is therefore the energy that's absorbed during breaking of the reactant molecules, plus the negative values which represent the energy released during the formation of the products, which gives minus 706 kilojoules per mole. This refers to per mole of carbon dioxide being formed. So this is already the molar enthalpy of the combustion of methane. We already clarified and explained that the enthalpy change during a chemical reaction is mostly dependent on the bond energies. However, although we spend a while doing the calculations, it is important to keep in mind that the theoretical values that are usually provided in textbooks and online, these are usually measured in accurate experiments rather than calculated. The measured values tend to be more accurate because they already account for energy changes during a chemical reaction that are in addition to the bond energies we considered during our calculations. There are several energy processes that occur in a chemical reaction, and therefore reasons for the discrepancy between the theoretical values for enthalpy change and the ones we calculate by using bond energies only. The first energy process that we haven't considered in our previous calculations is the energy involved in a state change of atoms and molecules. For example, the enthalpy of vaporizing water, which is the energy required to transform liquid water into a gaseous state, is 40.7 kilojoules for every mole of water. This is indeed an endothermic process, so energy needs to be absorbed in order to vaporize water. The reverse process, therefore, will release the same amount of energy because we are going backwards. When we did the calculation in the previous 2 examples, we did not consider the energy that would be absorbed or released when atoms and molecules change states. The second reason for the discrepancy between theoretical and calculated enthalpy change values is that bond energy that's used in calculations is usually provided as an average value. I'll explain this in more detail in a moment. And the third reason was briefly mentioned when we discussed the equation for enthalpy change. Enthalpy change includes the changes in internal energy of the system, which includes both the kinetic energy and the bond energy values, which we have considered, but also the pressure and changes in volume that occur during a chemical reaction. Although the changes in kinetic energy and volume are negligible compared to the bond energies, they will still contribute to a small discrepancy between the theoretical or actual enthalpy change values and the ones we calculate by only considering bond energy. Now, I want to return to the example of combustion methane and use this example to explain why changes in states of atoms and molecules will contribute to a different enthalpy change value. So the combustion methane starts off with methane and oxygen gas, and this will produce carbon dioxide and water. So we'll start with the reactants, and we'll absorb some amount of energy to break apart the methane molecule into the carbon and hydrogen atoms. And additional amounts of energy will be absorbed to break apart the oxygen molecules to give you oxygen atoms. So these two processes are both endothermic. Then the carbon and oxygen atoms will recombine together by forming bonds, and this will release energy. And similarly, when we are forming the water molecule, we are forming bonds between the hydrogen and oxygen atoms. This step is also exothermic. Now, the actual theoretical or measured enthalpy change value for this reaction is minus 802 kilojoules per mole of methane or per mole of carbon dioxide formed. The calculated value that we did in the calculation was slightly different, minus 706 kilojoules per mole. Now let's look at why the actual value, which is more accurate, compared to the calculated value are slightly different. Let's focus on this last process here, where we formed the molecule of water from the hydrogen and oxygen atoms. In this part of the chemical reaction, it is important to note that this step not only involves the formation of covalent bonds between oxygen and hydrogen atoms in the water molecule, it also involves the transition from gaseous water into liquid state water. Originally, these atoms are in a gaseous state because they originate from reactants that was methane and oxygen gas. The reactants were originally gaseous, so these atoms would have been in a gaseous state. So to form the water molecule, we will expect the water molecule to be initially gaseous, and therefore, if we want to transform the water molecule from a gaseous state into a liquid state, we need to condense the water molecules. And this process here is exothermic. It will release roughly minus 40 kilojoules of energy for every mole of water. Now, as you can see, this is the reason why there is a discrepancy between the actual measured value and the value that we calculated. This can be mostly accounted by the energy that will be released during the formation of water in the liquid state. Now, the second reason that we mentioned that could account for the discrepancy between experimental and theoretical values of enthalpy change is the idea of bond energy. In the table that provided values using the calculation, those were all average bond energy values. Let's consider a molecule methane again, which contains a carbon atom surrounded by 4 hydrogens. In most of the molecules, the first bond of the molecule usually will have the highest bond energy value. That means when you break this bond, it will require the most amount of energy. For this molecule, if we break this bond, we'll form a radical that is a single unpaired electron that stays with the carbon atom, and this will change the geometry of the entire molecule because the remaining bonds will move closer together towards the broken bond because there's fewer electrons here to cause the repulsion of these two bonds. So the breaking of bonds will destabilize the compound or the molecule by altering its geometry and the formation of the radical, which is a single unpaired electron. Now that this molecule has become more unstable, the second bond that we break will require less energy. So the bond energy here will be lower than the first bond. After we break the second bond, we again form another radical, and this will cause the remaining 2 unbroken bonds to again move towards them due to a smaller repulsion. So again, this will change the geometry and further destabilize the molecule. Subsequently, when we break the third bond, this will require even less energy and therefore have a lower bond energy value. So basically, subsequent identical bonds in a molecule, such as methane, will require subsequent lower amounts of energy to break apart. This is also true, but the reverse, for energy released during the formation of the molecule. This means the first bond that you form in the molecule will release the least amount of energy, followed by increasing amount of energy as you form more bonds and make that molecule more stable. Now, obviously, all of this is quite difficult to account for in calculations, which is why we always are provided with the average bond energy when calculating enthalpy change. Now, you can imagine by using the average value, it can result in slightly inaccurate values and therefore cause discrepancy between our calculations and the actual enthalpy change of the reaction. This concludes the video on enthalpy change and bond energy. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.